Lecture 29, Acids and Bases, Part 1, 1, Part 2. So in this one, we're going to talk about the strength of acids and bases and something called autoionization of water. All right? So what determines the strength of different acids? Okay, why are some acids stronger than others? Okay, we want to say that acids are strong because they want to lose that H+, but remember, they don't want to lose anything. It's all to be based on their forces of attraction of the salts, basically, right? So it's the force of attraction between the hydrogen and its conjugate base, basically. So we look at this. So acid strength will increase when moving down a group. So notice that as we move down, hydrofluoric acid is weaker than hydrochloric acid, which is weaker than hydrobromic acid, which is weaker than hydroiodic acid. Okay, so what all this is about is, remember, is as we move down a group in the periodic table, the energy level gets bigger and bigger and bigger. Okay, we have more energy level. So hydroiodic will have more energy level, okay, than hydrofluoric. Now, because the hydrogen is so far away from the nucleus, it's not held very strong. So because of that, the hydrogen can be donated very easily. So the iodine is not holding on to the hydrogen as strongly as the fluorine would be holding into its hydrogen. So because of the size of the iodine iodine atom, the hydrogen is not held very strongly, which means it will be released very easily. Okay, so that's why it makes it a strong acid. So the strong acid here increase as you go down a group in the periodic table. Okay, so its conjugate base would be the opposite. Remember, conjugate base is, we're looking at a base that's trying to pull in an electron. So as you saw, the fluorine, okay, hydrofluoric acid, it was a weak acid because it doesn't want to give up that H as easily. It becomes a strong base because now it has a more pull for that hydrogen that's floating around, okay, because the radius is smaller. So remember, a strong acid produces a weak conjugate base. A weak acid produces a strong conjugate base. So again, it all has to do with atomic radii and how far the nucleus or the hydrogen will be to compare to the nucleus of the conjugates. Now, there's another type of acid called oxoacid. Okay, oxoacid means there's a hydrogen involved in the middle. Okay, so there are two types of oxoacids. There's one, the hydroxide group. Okay, so here the hydroxide group in an oxide looks like this. Now the Y means there's another compound on it. So what we're focused on is these two right here. So in an oxoacid, we're not losing this OH. Okay, it's not a base. We're losing this H right here. So we're losing this H right here. That's the H that caused this to become an acid. Another oxoacid is a group bonded with a hydrogen. Okay, so here's that Y again. Here's a bunch of hydrogen. Again, there's this OH again. Okay, so again, remember, it's not the OH that's going to fall apart, but this H will dissociate, and that H caused this to become the acid. All right, so acid strength increases as the electronegativity of Y increases. So what's going to happen is the electronegativity of Y is going to increase, and because it's increased, it's going to make it the stronger pull toward the Y. And the stronger the pull is, the more tightly it's going to hold on to the H+. So the stronger the electronegativity of the Y is, the stronger the hole on this. That means the stronger the hole on the O, that makes the H easier to be released, okay, causing the acid to be strong. Okay, so the stronger the electronegativity of Y, it's going to pull on the on the O. The O is going to become a negative on this side and a positive on this side. And remember, H is positive, so the positive and positive won't be very liking to each other, so the H will fall apart. So with increased electronegativity in an oxoacid, there is an increase in acid strength. Okay, so here's an example of some oxoacid. Okay, so notice again, we have the O and I here, okay, the Br and the Cl. Now notice that electronegativity increases as you go up the periodic table, right? So Cl has got more electronegativity than Br, which is more electronegativity than I. So the Cl here is going to pull the electron closer to it from the oxygen, causing a dipole of a minus on this side. I'm sorry, a plus on this side and a minus on this side. Okay, so now that H is now going to have a problem. Okay, so now that H is going to be a problem, so it's going to be dropped off a lot easier than these guys will be. Okay, and because of that, it becomes a strong acid. So here's some other hydro. This is the one that has the 2 oxygen. Okay, again, it's the same idea. The only difference here is the more oxygen you attach to it, the more strength the acid will become. So notice in 1 oxygen, okay, you have the electronegativity this way. That hydrogen is your electron, your acid. Notice that as you increase the number of hydrogen, the concentration of the acid strength actually goes up. Carboxylic acid is another example of a weak acid. Okay, here again you have this OH. Remember, R is just a hydrocarbon group. Okay, so we have a double bond O, double H here. So these two are pretty much high electronegativity. It's going to pull this here. So this H is the one that is going to be released during the acid formation. Okay, so that is the H that makes carboxylic acid an acid. So carboxylic strength. Okay, notice that again, more electronegative elements that makes up R, the stronger the acid. So if this is a stronger electronegativity, then the stronger the acid will be. Okay, so here the CH3 has a weak electronegativity, so everything is pretty much balanced. So the hole on this H is going to be pretty strong, so it becomes a weak acid. However, the fluorine here is going to make this very electronegative. Okay, which means it's going to pull all the electrons toward here. So basically, what's going to do is going to make the hole on this H very weak. And because the hole on the H is very weak, it is easily released from this compound to create the acid that we saw. Okay, so there's a process called autoionization of water. What that means is in water, we have H2O. But remember, water can also act as an acid and a base. So what happened is water will auto-ionize themselves, which means some of them will break up that H to become the hydronium, the hydronium ion, the H3O plus, and then the others will become the OH minus, and then they repeat this process back into water. So this process repeat. And they do this all by themselves at a constant of 1 times 10 to the negative 14. Now notice that Kw, K is that equilibrium constant again, remember? Okay, so we're going to throw in the equilibrium constant again. Now this is going to be very useful later when we do pHs and how to determine pH and things like that. So if you look at the ionization of water, the concentration of OH in solution is found to be 1.4 times 10 to the 11 molar at 25 degrees C. Find the concentration of the H3O. So again, we know the equilibrium constant for the self-ionization of water, and we know the concentration of the OH, which is that one, and we know that the whole thing, okay, the Kw is 1 times 10 to the negative 14. So by manipulating the formula, we can find the concentration of the H3O plus, which is 7.1 times 10 to the negative 4. Okay. So here's an acid-base equation can be written very simply as this, right? So this is more like the net equation. So H of A, so that's the acid. This is the conjugate base part. Water makes H3O plus the conjugate base, or just HA plus H plus and this. So we don't have to write the H2O. This is one way to write it. This is the other way. Okay. Remember, H plus, which is the hydrogen ion, is the same as hydronium, which is the same thing as H3O plus. Again, if you have any question, make sure you ask in class.